Hello, pre-calculus students. This is the notes for 5.1b. Now, the first part here, 65 through 70, are all pretty easy as soon as you learn one little trick. And 67, 69, 68, and 70 all have one thing in common. And that requires a little trick that has to do with the base here. The problem with this particular problem hang on, let me pause this for a second. So if this were reversed, it'd be a little easier to work on, but because this denominator is a mess, I can't split denominators up. But I can make this simpler if I take a look at my identities page. The identities page that's connected to the website, which looks like this. If I notice one of the identities over here on the Pythagorean is 1 minus cosine squared u equals sine squared u. That's the key one. If I could just get that 1 minus cosine to look like 1 minus cosine squared, then we'd be good. And I can if I multiply both the denominator and the numerator by the conjugate of the denominator. So that's what I'm going to do. I'm going to multiply both the top and the bottom times 1 plus cosine y. By doing so on the top, I'm keeping the bottom balanced. By doing so on the bottom, because this is basically a minus b times a plus b, I'm going to get the difference of 2 squared. So on the top, I get sine squared times 1 plus cosine. It's really hard to write on this computer this way. And then on the bottom, I get 1 minus cosine y squared. But 1 minus cosine squared is sine squared. So now I get sine squared y over sine squared. And keeping in mind that on the top, I still got that 1 plus cosine up there. But now, since the sine squareds will cancel, I'm left with 1 plus cosine y, which is a lot easier to look at than the initial problem. All right, that's easy enough. Now, these particular problems, it says to use a graphing utility to determine which of the 6 trig functions is equal to the expression, then verify your answer algebraically. I'd prefer you reverse that first you try to do the algebra and then see if it's what you thought it was. So on 75, we've got the cosine of x times the cotangent of x plus the sine of x. So I remember the cotangent is the cosine over the cosine over the sine. So what that's going to do is that the cosine can be rewritten as cosine over 1. So cosine of over 1, cosine of x. Cosine x times cosine x is cosine squared. Well, what a drag. If this had only said cosine squared x over sine plus sine squared x over sine. Wait a minute, couldn't I just multiply that times sine over sine? If I do that, now I get sine squared x on the top and sine on the bottom. And now I get cosine squared x plus sine squared x over sine x. Well, cosine squared plus sine squared, same thing as sine squared plus cosine squared. This isn't sine squared, it's just sine. Is 1. So I end up with 1 over sine of x. And what's 1 over sine of x equal to? Yep, cosecant x. So if we did our work right, this should look like the cosecant. Let's see. I'll go to Desmos. And this is what was originally written in. And that's what I get. And it sure looks like it's the cosecant. Let's see if it is. Yep, that's what it is. Look at that. That's what it is. Well, that worked out. Okay, now trigonometric substitution is actually really, really simple, and I'm always a little shocked at how difficult students try to make this. All we're doing is we're going to replace x with what it's equal to, and they tell us what it's equal to in this case. And they also tell us that the answers we're looking for are in the first quadrant, so everybody's going to be positive. So we're going to get the square root of 25 minus parentheses 5 sine theta quantity squared. Well, that is equal to the square root of 25. Keeping in mind, we can't take the square root of any part of this right now because this is 2 terms. Well, 2 terms can't be square rooted easily. We end up with really nasty radicals. So, but I can square this now, and I get 25, because 5 times 5 is 25, and sine times sine is sine squared, which you notice quite quickly that I can factor out at 25. Well, that you can take the square root of now, because it's a factor. And then the rest of it is 1 minus sine squared. Well, wait a minute. We just discussed this a minute ago. What's 1 minus sine squared equal to? Cosine squared. So we get 25 cosine squared, which now it's just a product. And I can take the square root of a product, especially if they're both perfect squares like this. The answer is 5 cosine theta. Now, I know some of you are smart enough that you could look at that and say, oh, I know what it is, 5 cosine theta. Great, you still got to show the work. Remember that Einstein, smartest man in the world, failed college math because he wouldn't show his work. He later went on to teach that class, but it didn't change the fact that he failed that class because he didn't show his work. Anyway, you can show your work and you'll be fine. Now this looks really complicated, but it isn't. In fact, some of you are immediately going, oh, it's logs, oh, it's subtract. This isn't hard at all. So why are they putting these absolute value there? Because remember, you can't take the log of a negative. But there is a problem I have with this. You also can't take the log of a 0. And this will sometimes produce a 0 the way it's written, so it's like not really good enough. And there's no easy way to say it, but what they should say is that sine theta and cosine theta are positive numbers. And then that would save that problem. But we know the rule, so this is for number 95, that if I have the log of a difference, it's the same thing as saying the log of a quotient. So I would get cosine on top of sine. And if you look on our trigonometrics identity page, we know that the cosine over the sine is the, drumroll please, cotangent. Now, if we're going to be fair, those guys were in absolute value symbols. So guess what this guy's in? Absolute value. Saves us from getting a negative. And that's all you do. So it's not like it's tough. You can do this, right? Now I'm kind of embarrassed to do this one because you should know this stuff from Algebra 2. But let's do a little reminder. So on number 119, in order for me to add those two unlike denominator fractions, I've got to give them the same denominator. Now I'm just going to write it as one big fat fraction. And the big fat fraction has a denominator of x plus 5 times x minus 8, which means this one has to be multiplied by x minus 8 on the top and the bottom. That gives me the bottom. All right, and then I'm going to get 1 times x minus 8, which is going to give me x minus 8. And then this one has to be multiplied by x plus 5 times x plus 5, which gives us x times x plus 5. And technically, we've completed what's been asked of us, which is to perform the addition or subtraction. But now we haven't simplified it, so we got to simplify it. So what's x times x plus 5? Well, it's x squared plus 5x. And then we've got another x and a negative 8. That's a really sad 8, isn't it? And on the bottom, I'm going to end up with x squared plus 5x minus 8x minus 40. So that finally gives me on the top x squared plus 6x minus 8, and on the bottom x squared minus 3x minus 40. Let me pause that for just a second. Okay, that's the answer, but the book doesn't bother multiplying these two together. So it would be x squared plus 6x minus 8 over x plus 5 times x minus 8. But this method, this way of writing it is just as good. So you can figure out the others. Don't forget that the relationship between this one and this one is that they are opposites, which means in order for me to get the same denominator, I've got to multiply something by negative 1 over negative 1. And in this case, they have no factors in common, do they? So we'll take a little more work.